This video, I'll be working out the solution of the test study guide. Let's begin with number 1. The null and alternative hypotheses are given. Determine whether the test is left, right, or two-tailed test. Okay, so you can see the null hypothesis is mean equals 9.9 and the alternative mean not equal to 9.9. When you want to check if a test is right-tailed or left or two-tailed test, you look at the alternative. If the sign in the alternative is less than, it is a left-tailed test. If the sign is greater than, then it is a right-tailed test. And if it's not equal, it's a two-tailed test. And the parameter that we are testing here is the mean. Number 2, the mean repair bill of cars is greater than 110. Write the null and the alternative hypotheses. Greater than should go to the alternative hypothesis, and the null hypothesis is a statement of equality always. So H1 will be mean greater than 110, and this is what the claim is. And mean equals 110 is the null hypothesis. Number 3, a referendum for an upcoming election is favored by more than half of the voters. Identify the type 1 and type 2 errors for the hypothesis test of this claim. So someone is making a claim that the referendum is favored by more than half of the voters. So I wrote the null and the alternative. H1 will be P greater than 0.5, which is half, 50%. And the null will be P equals 0.5. What is type 1 error? Type 1 error occurs when we reject the null hypothesis when it is in fact true. So you're rejecting something that is true. That is, we reject HO and support H1 when P is not actually greater than 0.5. So we are saying here that the majority of the voters are favoring the referendum when this is in fact, it's not the case. This is a type 1 error. What would be type 2 error? Type 2 error occurs when we fail to reject the null hypothesis when it is false. So, meaning we make a conclusion that P equals 0.5 or less when in fact, P is greater than 0.5. That is a type 2 error. Number 4. If we don't reject the null hypothesis when the null hypothesis is in error, means it is false. What type of error did we commit? It's a type 2. Number 5. Let me show you number 5 right here. The mean age of principals in a local school district is 53.6 years. So I wrote the null and the alternative hypothesis. Mean equal 53.6. You can see here. And alternative will be mean not equal 53.6. And you understand why I put the claim and the null hypothesis, because it says is, and is means equal, which is a statement of equality. Any statement of equality will go to the null hypothesis. If a hypothesis test is performed, how would you interpret the decision that rejects the null hypothesis? So if we reject the null hypothesis right here, that means we are rejecting the claim, because the claim is the null hypothesis. So we say there is sufficient evidence to reject the claim that the mean age of principal in the local school district is 53.6. Instead of sufficient, you can use the word enough. Number 6. The dean of a major university claims that the mean number of hours the students study at her university per day is more than 4.2 hours. So I've written the null and the alternative hypothesis here. H1 will be mean greater than 4.2. HO will be mean equals 4.2, and the claim is in the alternative. If a hypothesis test is performed, how should you interpret the decision that fails to reject the null hypothesis? If we cannot reject the null hypothesis and the claim is in the alternative, that means we cannot support the claim because we couldn't reject the null hypothesis. So we say, every time that you fail to reject the null hypothesis, you have to start with this. There is not enough evidence to support the claim that the mean number of hours students study per day is more than 4.2 hours. What about if we reject HO? What do we say here? If we reject HO, we say there is enough evidence to support the claim. Okay. Next question. An airline claims that no-show rate for passengers is less than 5%. So the percent of passengers who don't show up to their flight is less than 5%. So this is a proportion test. In a sample of 420 randomly selected reservations, 19 were no-shows. So the number of observations here is 420, and the number of successes X is 19. At alpha equals 0.01, test the airline's claim. So here's how we get started. We state the null and the alternative hypothesis. So P is less than 0.05, which is 5%, and that's the claim. And HO P equals 0.05. We have X, the number of successes, which is 19, and we have N, the number of observations. We're going to go to StatCrunch and run a proportion stats test in StatCrunch. So we're in StatCrunch. You go to Stat, Proportion Stats, one sample with summary. Number of successes is 19. Number of observations 420. Now, what we're testing that P is less than 0.05, so we need to change this to 0.05. And if you want to see the p-value, you can select it right here. And let me show you the compute button that you have to press on. And let me just take this inside the recording area. There we go. So Z is negative 0.45 and P is 0.3272. Well, P is going to be bigger than alpha, so we're going to fail to reject HO. And let me show you the sketch of the P value. It's going to be an area to the left of Z equal negative 0.45. When you see too much shading under the curve means P value is large, then you're going to fail to reject the null hypothesis. So Z is negative 0.45. P value is 0.3264, which is bigger than alpha. We fail to reject HO. If you fail to reject HO and the claim is in H1, you cannot support the claim. So you say there is not enough evidence at the 1% level of significance to support the airline's claim that the no-show rate for passengers is less than 5%. Next question. A local retailer claims that the mean waiting time is less than 9 minutes. So if I now write the null and the alternative hypothesis, it will be in the alternative H1 mean is less than 9 minutes. That's the claim. And HO will be mean equals 9 minutes. A random sample of 20 waiting time, so N is 20, has a mean of 7.4. That's X bar. Sample mean X bar 7.4 minutes with a standard deviation of 2.1. That's S. At alpha equal 1%, test the retailer's claim. Assume that the distribution is normally distributed. Round the test statistic to the nearest thousand. So he wants the test statistic with 3 decimal places. So we're going to go to StatCrunch and run a t-stats there. So we are in StatCrunch, stat, t-stats, one sample with summary, sample mean, which is 7.4, sample standard deviation 2.1, sample size is how many? 20 in the sample, and we're testing against the value 9, and we're testing if the mean is less than 9. Let me just show you here. If you want to see the p-value, you can sketch it. And we're gonna hit compute. And here's what we get. We get T to be negative 3.407 and the p-value is 0.0015. So T is negative 3.407, p-value is 0.005, as you can see here. So, which is less than alpha, we're going to end up rejecting the null hypothesis. And if you reject the null hypothesis and the claim is in the alternative, you support the claim. There is enough evidence at the 1% level of significance to support the claim that the mean waiting time is less than 9 minutes. In 2010, the mean for the number of pets owned per household was 1.9. A poll of 32 households, so N is 32, conducted this year reported that the mean for the number of pets owned per household to be 1.8. So X bar is 1.8. Assuming sigma equals 1.1. I want to pause here. And when I say sigma, I'm giving you the population standard deviation. And when I give you the population standard deviation, you cannot use a t-test or a t-stats. You have to use z-stats. Only when sigma is given, the population standard deviation. Is there sufficient evidence to support the claim that the mean number of pets owned has changed since 2010? Has changed, guys, means not equal to. So it was 1.9. We want to see if it's not equal to 1.9 anymore. So that will be HO will be mean equals 1.9 and H1 will be mean not equal to 1.9, and that's the claim. We have N equals 32. We have the sample mean to be 1.8. We have sigma to be 1.1. And we have the level of significance alpha that we would be comparing the p-value to be 10%. So we're going to go to z-stats, one sample with summary, and let me show you how to do that. So this is, you go to stat, z-stats, one sample with summary. Sample mean, the sample mean here is 1.8. Standard deviation is 1.1. N I have 32. And we're testing against 1.9. Equal, not equal, so I got the right ones. And if you guys want to see the p-value, you can just select that one, and we're going to hit compute right now. So z will be negative 0.51, and the p-value is 0.6071. That's a huge, so you're going to fail to reject HO. And let me show you the p-value on both sides. It's going to be lots of shading in red under the curve. This part, and this part's supposed to be shaded, but the program doesn't shade it, but he's shown you a vertical line, and that's a shaded region to the left of it as well, so in both sides. Okay, so z is negative 0.51, step number 2. Step number 3, p-value is 0.6071, which is bigger than alpha, so we fail to reject HO. And guys, when you fail to reject the null hypothesis, you cannot support the claim if it is in H1. So we say there's not enough evidence at the 10% level of significance to support the claim that the mean number of pets owned has changed. Next question, now we're working with 2 samples. Classify the 2 given samples as independent or dependent. Sample 1, pre-training blood pressure of 11 people, post-training blood pressure of the same 11 people. Well, if it is the same group before and after action, the samples are dependent or paired samples, so they are dependent samples. Next question. To test the effectiveness of a new drug designed to relieve flu symptoms, 200 patients were randomly selected and divided into 2 equal groups. One group of 100 patients was given a pill containing the drug, while the other group of 100 was given a placebo, water pill. What can we conclude about the effectiveness of the drug if 62, so out of the first 100, 62 of those actually taking the drug felt a beneficial effect? And while the other group who took a placebo, only 41 of the patients taking the placebo felt a beneficial effect. Use alpha equal 5%. So now we have 2 proportions, and we want to see if the drug was effective. That means the proportion who felt the benefit by taking the drug is more than the proportion who felt the benefit by not taking anything. So we need to test that P1 is greater than P2, as you can see right here. Let me just keep the question right here. We're testing that P1 is greater than P2. The null hypothesis, as you know, is a statement of equality, so it will remain P1 equals P2. We're gonna run proportion stats here, but not with one sample anymore. It's gonna be two samples, and let me show you how to do that. So we go to stat, proportion stat, two sample with summary. Number of successes is 62. So the ones who felt the benefit from taking the drug. Number of observation, 100. Number of successes, 41. And number of observation is 100. We're testing that P1 is greater than P2. All you have to do, guys, don't touch the zero here. We need to test that P1 minus P2 is greater than zero. P1 minus P2 greater than zero is the same thing as P1 greater than P2. So just leave it as is. And you can, if you want to see the p-value in action, you can select it right here, p-value plot, and then I'm gonna hit compute and get the results. You can see z is 2.97 and p-value is so small, so we're gonna reject the null hypothesis. And let me show you the p-value. You're not gonna see much shading because it's a very small area. It's right here. You see that little bit of red right here shaded, okay? So z is 2.97, p-value is 0.0015. We reject HO because this p-value is less than alpha, which is 5%, and then support the claim. There is enough evidence at the 5% level of significance to support the claim that the drug was effective in relieving the symptoms of flu. Next question. A physician claims that a person's diastolic blood pressure can be lowered if instead of taking a drug, the person mediates each evening. 10 subjects are randomly selected and pre-tested. Their blood pressures measured in millimeters of mercury are listed below. The 10 patients are instructed in basic meditation and told to practice it each evening for 1 month. At the end of the month, their blood pressures are taken again. The data are listed below. Test the physician's claim. So the physician is making a claim. As a result of meditations, patients can lower their diastolic blood pressure. Okay, here's what you're gonna do here. Since those samples are dependent, when you see a table with 3 rows and one it says before and one it says after, you know they are pair dependent, you have to test the hypothesis here in a different way, not like the way we do it with independent samples. So this is how we do it. We're going to do the differences. So for patient 1, 85, it was 85 and now it's down to 82. So 85 minus 82 is 3. Did it work for patient number 1? It did work for patient number 1, as you notice. So you know what I'm going to put here? I'm going to put a yes for patient 1. Right under 3. What about patient number 2? It went down from 96 to 90. Did it work? The answer is yes. What about patient number 3? No change. No, it didn't work. What about patient number 4? From 83 to 75. The difference is 8. It did work. Patient number 5. 80 to 74. Yes. Patient number 6, the difference is 11, yes. Patient number 7, it didn't work, actually it went back up, so that's a no here. Patient number 8, from 98 to 88, it's a yes. Patient number 9, 93 minus 98 is a yes. Oh, 93 minus 89, so it's a yes for. And then patient number 10 is 96 minus 80, it did work. Okay, here's how I'm going to show you how to figure out, just a sign of the alternative hypothesis. We're going to test whether this mean of the difference is positive or negative, but this is how you can tell. Where you have the yeses, you see the differences. Do you agree with me that all those differences above the yeses are positive? That means we need to test that the mean of the difference is greater than 0. And that's what I put here. I put mean of the difference. This is how we write it down, mu, and then little d. greater than 0, and that's the claim. And as you know, the alternative hypothesis is always a sign of equality. You put equal to 0. What we're going to do, we're going to take those differences and put them in StatCrunch and run a t-stats test against the value 0 right here. Okay? Okay, let's go to StatCrunch. There they are. I put the differences in there, so we're going to go to stat, t-stats, one sample with data, not with summary. I have the actual data right here. Okay, I call it D, so I'm going to select D right here. And just one sec. Okay, we need to test that the mean of the difference is greater than 0. And if you like to see it to show the p-value, you can do a p-value plot right here. So we got the test statistics to be 3.49, 0, and p-value is 0.0034, which is less than alpha. Then you're going to reject the null hypothesis and support the claim. So t is 3.490 again. P-value is 0.0034, which is of course less than alpha. Sorry, alpha here is 0.01. So we reject the null hypothesis and we support the claim. There is enough evidence at the 0.01 level of significance to support the claim that a person's diastolic blood pressure can be lowered using the meditation program. For the remaining questions in the study guide, please watch the second video. I'm going to make it in 2 videos here.